I want to talk a little bit about conservative forces and the potential energy. We have seen that the kinetic energy of a moving object is equal to 1/2 its mass times its velocity squared. And we also have worked with the work-energy relation in terms of the kinetic energy that tells us that the change in the kinetic energy will be equal to the work of all forces before we have started splitting and separating them into two groups of conservative or non-conservative forces. The mechanical energy is defined as the sum of the kinetic and the potential energy. And in terms of the mechanical energy, the work-energy relation actually looks slightly different. The change in the total mechanical energy is equal to the work of only the non-conservative forces. So here we have ignored the work of the conservative forces on the right-hand side of the equation. So why do we really have to work energy relations, and what good is it, and which one should we use, and what's the difference? So let's look at the total mechanical energy. The change in total mechanical energy will be equal to the change in the kinetic plus the change in the potential. And because of the work-energy relation, we will have that total change has to be equal to the work of the non-conservative forces. But if I move the change in the potential energy on the right-hand side of the equation, I can actually see that the change in the kinetic energy will have to always be equal to the work of the non-conservative forces minus the change in the potential energy. On the other hand, I have that work-energy relation here from above that says that the total change in the kinetic energy has to be equal to the work of all forces. So I can see that this term here, which is the negative of the change in the potential energy, must be the effect of the conservative forces, right? When you add up the effect of the conservative forces and the non-conservative forces, you end up with the effect of all forces. So we can see here that the potential energy associated is related or associated with the conservative forces. If we have one conservative force, you'll have one potential energy. If you have more conservative forces, you'll have potential energy functions for each of those forces. And we can write that the change of the potential energy associated with the conservative force has to be equal to the minus of the work of that particular conservative force. In mechanics, especially in the introductory level of physics, you can expect more or less to see only two conservative forces: the gravitational force, for which we know it's a mg, and we have the gravitational potential energy equal to mgy. That expression applies only for situations very close to the surface of the Earth. And the elastic force of a spring, for which we have Hooke's law, and the elastic potential energy is given by the expression of 1/2 kx squared. So we see those functions were not just some arbitrary functions, but they were chosen so that the relationship between the potential energy and the work done by that force stands. Or in other words, the change in the potential energy has to always be equal to minus the work of that conservative force. Now remember that in the most general case, the work actually involves integration. So we need to use calculus to figure out what the work is in one dimension, or generally we can write integral of f dl times cosine theta in 3 dimensions. If we know the components of the vectors for the force and for the displacement, we can actually calculate the integral of fx dx, fy dy, plus fz dz. So we can see that given that the potential energy is going to be minus that work, there's a relationship between any conservative force and the potential energy associated with that force. In other words, the change in the potential energy will always be equal to minus the work, or minus the integral of f dl cosine theta, or minus the integral of fx dx plus fy dy plus fz dz. Now, I haven't included any examples from this topic, but just for completeness, if you find yourself in a situation where someone has given you the function for the energy and you need to figure out what was that original conservative force with which that potential energy was associated, you have to perform an operation that is reverse to integration. And you know from calculus that the reverse to integration is differentiation. So if someone gives you the function for the potential energy, you actually have to find the derivative of that expression. Don't forget the minus, it's one of the most common mistakes mistakes here on homework and tests in my class. So the x component of the force will always be equal to minus the derivative of the potential energy with respect to x. And you might actually have two other variables, y and z, in that function, but you have to treat them as constant. In other words, just ignore the variables and treat them as constants. Similarly, if you need to figure out the y component, then you have to calculate the derivative with respect to y, take it with minus, and again treat x and z not as variables but as constants, and the z component, you probably can guess, will be the minus the derivative of u with respect to z. Again, keep x and y, treat them as constants. So what are those conservative and non-conservative forces, and why do we have to separate the forces into two categories? What's so special about that? So let's consider an object that actually moves from point A to point B. And then that object goes back from B to A. And during that movement, there was some force that acted on it. So I can look, if that force was a conservative force, I can look at the work of that force that it did while the object was moving along the curved path on its way from A to B. And then on its return, even though it's not the same path, but it just took a straight path from B to A, I can also look at the work of that force that it did during that displacement from B to A. If that force is a conservative force, you will find out that the sum of the two works is always identical to zero. Not more or less, not approximately, not good enough, but it all, in a sense, it cancels out. So whatever that, for conservative forces, whatever they do along the path, they will undo that if you go back to where you started, and you don't even have to backtrace identical your path in the same fashion. You just have to go back to your original point. So it turns out that it's actually more handy and convenient to work with the concept of potential energy that we associate with the work of such forces. It is perfectly possible to solve all the physics problems from the introductory physics without the concept of the potential energy. You just have to calculate the work of the conservative forces. But my experience is that the questions are much more easily solved and somehow much more intuitive if you invest in that effort to become familiar with the concept of potential energy. I like to use potential energy any day over calculating the work of a conservative force. So once again, the definition of potential energy here, once we have identified the conservative force, is that the change in that potential energy has to be equal to minus the work of the conservative force. In mechanics, in 99% of the cases, you will be dealing with only two conservative forces. One is the gravitational force, and we count the gravitational potential energy. This is in situations where we have objects that change their vertical elevation, maybe a rock falling down or a roller coaster. We have the gravitational force near the surface of the Earth is approximately mg. So potential energy for any situations and problems that involve objects near the surface of the Earth will be mgy. The second situation is the elastic spring. So if we're working with a spring, with ideal spring, we will know that the elastic force here is given by Hooke's law, F is equal to minus kx, and that too is a conservative force. And so we associate a potential energy with it, which is 1/2 of kx squared. What about the non-conservative forces? Well, usually what I do is like I count which are the conservative forces, and then everything else is non-conservative forces. In mechanics, again, in 99% of the cases, it will be you discard gravity and elastic force of a spring, and everything else that you see as a force in your problem most likely is a non-conservative forces, non-conservative force. For those non-conservative forces, you can go from point A to point B and calculate the work of that force, and then you can come back from B to A and calculate the work from the work of that force, but it will not add up to zero. Even if you very carefully backtrace your path, it will still not add up to zero. In other words, you cannot cancel their effect. Here's a classic example, friction from mechanics. Friction is a non-conservative force. Imagine you slide from A to B along the curved path, and you know that friction is going to take away some of your energy, so that means the work will be zero. then you can slide back if you wish along the same path, but the friction is never going to give you back that energy. Once again, on the way back, it will remove even more energy from you. So overall, when you add the two effects on the way there and back, you will see that friction will be, that the work of friction will be always negative. We say friction always removes energy from the system. In other words, it converts it in fact into kinetic energy of the molecules surrounding the system. So it's not like it's destroying energy. So we still can trace the energy. We still have that very big concept in physics about conservation of energy. But on practical level, it's virtually impossible to catch all the molecules, bring them back, extract the amount that they got from the system. And because of that, it's easier and more practical to cut our losses and say that the friction took away the energy and we just count it as a loss. Again, that is not to destroy that energy. Is still in our universe. It's just in a form that we can't have access to it.